All right, section 7.3, we are introducing the idea of a logarithm. So we're going to look at logarithmic functions as inverses. Our objectives today are to write and evaluate logarithmic expressions, and then tomorrow we'll look at graphing log functions. So, first question here. I have given you some numbers. I want you to convert them to using a base of 2 or 3. In other words, 8 can be expressed as 2 to the third power. Right? 27 can be expressed as 3 to the third power. Now, for a 12, we are trying to express it as 2 to some power, but I don't know what that power should be. I do know that for 16, I have 2 to the fourth. And if I know that 16 gives me 2 to the fourth, and 8 is 2 to the third, then 12 has to be somewhere in between there. So that tells me that this power that I'm looking for here has to be between a 3 and a 4. Okay, it's going to be a decimal number somewhere in between there. The same thing with our 3's. 81 is 3 to the fourth, and 27 we said was 3 cubed. So 42 is going to have to be 3 to some power in between a 3 and a 4. In this lesson, we're going to learn how to express all those numbers as powers using a common base. All right, the definition of a logarithm. It says a logarithm of base b of a positive number x satisfies the following definition. For b, the base being greater than 0 and not equal to 1, the log base b of x is equal to y if and only if b to the y equals x. In other words, the logarithm y, all right, so y was a logarithm, it is the power that we need to raise b to in order to get x. So when we talk about finding a log, we're looking for a power. We're trying to find that power. Just like up here, we were trying to find this missing power. Logarithms basically undo bases with unknown powers. All right, so we're going to be using logs to find those unknown powers. The exponent y in the expression b to the y is the logarithm in the equation log base b of x equals y. So y is the log, which means it's the power here. Okay? The base in b to the y and the base in log base b of x are the same. In both cases, that base cannot equal 1, and it has to be positive. Since b can't equal 1 and it has to be positive, anytime we take a number here, raise it to a power, if this number is positive, then our base to a power will always be positive as well. Since b to the y equals x, and x has to be greater than 0, so log base b of x is defined only for x greater than or equal to 0. And we're going to encounter that a little more tomorrow when we start looking at the graphs of logs. Because y equals b to the x and y equals log base b of x are inverse functions. Okay? So this function and this function are inverses of each other. We've talked in the past when we do compositions of inverses, we are going to basically undo each other. So we end up getting back to a. If we look at this one first, it says log base b of b to the power a is equal to a. When we talk about a logarithm, we said log base b of x equals y if and only if b to the y power will get us back to x. Okay? So if we think of this, we're saying our base b to this power of a gets us back to here. All right? It makes sense. Log base b of b to a power is just going to be the power. Our other statement here says b raised to log base b of a is also a. In other words, they're going to undo each other. We'll look at those a little bit more in our next section when we start talking about the properties, all the properties of logs. We're going to start here by writing an equation, a statement, in logarithmic form. So if we know that 10 squared is equal to 100, we can rewrite that in log form, saying log base 10 In our example here, 10 is the base. It's being raised to the power 2. Log base 10 of something has to give me the power. The answer in a log statement, what we put over here, is always the power. And in this example, our power is 2. So we are saying log base 10 of 100 equals 2. We often think of just kind of circling around here, because another way of checking this, we say 10 to this power has to get us back to that. And that's true. 10 squared does equal 100. Okay? So we're not solving anything here. We're just rewriting it. This is in exponential form. This is in log form. All right. Our next one. We know that 3 to the 4th equals 81. So we can write that log base. So in this case, the 3 is our base. The answer, the power, is 4. So we are taking log base 3 of 81 and getting a power of 4. Again, checking it, 3 to the 4th power has to give us 81. All right, I'm going to pause the recording. I want you to try this next one. All right. Rewriting it in log form. Log, our base is 6, so log base 6. Our power, our answer is a 2. So we are saying log base 6 of 36 should give us 2. All right, our next one has some fractions. It doesn't matter. We still have a base here of 2/3 being raised to a power of 3. So log with our base of 2/3. Our power or answer is supposed to be 3. What we're taking the log of is 8/27. And our last one, we have 1 is equal to 3 to the 0. So we can rewrite that. Log base 3, we get an answer of 0 when we take the log of 1. Log base 3 of 1 is equal to 0. All right, we're going to set up these next ones to actually simplify them. It says, what is the value of log base 8 of 32? All right, so we're trying to find x. We are going to do our little circle and rewrite it exponentially. So we can say that our base 8 raised to this unknown power is supposed to get me to 32. Now, 8 raised to a power gives us 32. We can't write 32 as 8 to a power. But we can convert both the 8 and the 32 into a common base. Both of them can be written as 2 to a power. So 8 is 2 cubed. It's being raised to the x power. On the other side, 32 is 2 to the 5th. And if our bases match, and they're equal, then our powers have to match. So simplifying this, we have 2 to the 3rd, and then that raised to the x power. That's the same as saying 2 to the 3x equals 2 to the 5th. These have to be equal. So 3x has to equal 5, which means x, this missing power that we're looking for, would be a 5/3. All right, our next one. Log base 5 of 125. We're trying to figure out what that equals. So we do our little circle and we rewrite it exponentially. So the exponential form of this log statement would be 5 to some power equals 125. Again, we want to try to convert them to a common base. We don't have to change the 5 on the left side here because we can write 125 as 5 to the 3rd. And since they are equal with the same base, these powers have to be equal, which means x would have to be 3. For our next one, log base 4 of 32 equals something. So 4 to some unknown power has to give us 32. Okay? We are going to convert this to a common base. 4 and 32 are both powers of 2. So I'm going to rewrite 4 as 2 squared. And 2 squared to the x power is just the same as 2 to the 2x. 32 is 2 to the 5th. Again, we have a common base. That means our powers have to be equal. So 2x has to equal 5, and our unknown power would be 5/2 or 2.5. All right, our next one, we have log base 64 of 1/32 equals something. So again, doing our circle, we're saying 64 to some power gives us 1/32. All right, 64 and 32. If you look at your power charts, those are both powers of 2. So 64 is the same as 2 to the 6th. We're raising that to the x power, so we have 2 to the 6x. Now, 32, we've already talked about that one. 32 is 2 to the 5th, but because it's in the denominator, we're going to have to flip that up and make that 2 to the -5. Okay? So now we have the statement that 6x has to equal -5. So x is going to be -5/6. All right. A common logarithm is a logarithm that has a base 10. If it helps you at all, you can certainly write log base 10, but to shorten things up, we often change log base 10 and we just write log of x. All right, so if you want to put the little base in there, it is a 10. You can do that. If you don't see a base, the assumption is it's a common log, and we are using a base 10. All right, many measurements of physical phenomena have such a wide range of values that the reported measurements are logarithms or exponents of the values, not the values themselves. When you use the logarithm of a quantity instead of the quantity, you are using a logarithmic scale. The most common one that people have heard of is that Richter scale. It's a log scale used to measure the magnitude of an earthquake. So in our example here, for each increase of 1 in the Richter scale, we are basically saying that this energy, excuse me, the energy is getting multiplied by a 30. So if I'm comparing an earthquake with a magnitude of 4 to an earthquake with a magnitude of 3, this one is 30 times bigger. All right. Example 3. It says in December of 2004, an earthquake with magnitude 9.3 on the Richter scale hit off the northwest coast of Sumatra. The diagram shows the magnitude of an earthquake that hit Sumatra in March of 2005. The formula, log of I sub 1 divided by I sub 2 equals m1 minus m2, compares the intensity levels of the earthquakes, where I is the intensity level determined by a seismograph, and m is the value of the Richter scale magnitude. How many times more intense was the December earthquake compared to the March earthquake? All right, so we know that in December it was a 9.3. In March it was an 8.7. All right, that's given to me over here in the picture. We are comparing December to March. All right, so December is going to be our first value, March will be our second value. So we can fill in our formula. Log, and notice there's no base, so we're talking log base 10. I sub 1, the intensity of the December one, compared to the intensity of the March one, is the difference between their magnitudes. So 9.3 minus 8.7. Simplifying that, 9.3 minus 8.7. We can say the log of I sub 1 divided by I sub 2 is 0.6. Now we're going to rewrite it exponentially. I want you to picture there being a little 10 as the base, since we are using a common log. 10 to that power has to get us back to this. So we can write that as 10 to the 0.6 power is the comparison of their two intensities. All right, grab your calculators. 10 to the 0.6 we should end up with something around a 4. That means the December earthquake is 4 times bigger than the March earthquake. All right, go ahead and pause the recording and try this next one. All right, let's check. In 1995, an earthquake in Mexico registered 8.0 on the Richter scale. So in 1995, we were at an 8.0. In 2001, an earthquake of magnitude 6.8 shook Washington State. How many times more intense was the 1995 earthquake compared to the 2001 earthquake? So again, we're going to think of this as our first value, and this is our second value in our formula. So we have log of I sub 1 divided by I sub 2 equals m1 minus m2. So our first value was an 8.0. Our second was 6.8. (8.0) minus 6.8 is 1.2. All right, converting that into its exponential form. Remember, there's a base of 10. So 10 to that power gives us that. So 10 to the 1.2 power is the comparison of their strengths or intensities. And that should end up being about a 16. Okay, so the 1995 earthquake was about 16 times stronger than the 2001 earthquake. All right, so just an example of where you might see logs being used and that logarithmic scale that we call the Richter scale. All right, for tonight, you are going to do page 456, questions 12 through 35, 46 to 50, 85 to 88, and 95 to 98. Remember, in a log statement, if you have log base b of something equals y, we can rewrite that in exponential form. This is an equivalent form. Okay? These mean the same thing, they're just written in two different formats. To convert it, we just do our little circle. We start with our base, we raise it to our power. Remember, the answer in a log statement is a power. So we have b to the y power, and it has to get us back to x. So I want you to get used to going back and forth between that log form and exponential form.